Good morning, everybody. Welcome to our machine learning seminar, which I co-chair together with Elisa. Elisa, if you could say a few words about the speaker and continue, that would be great.
Awesome. Good morning, everyone. Today we have Abir as a speaker who will be giving an exciting talk about voice biomarkers, which is a really hot topic in the area of digital health. She's a third-year PhD student at the LIH, so the Luxembourg Institute of Health, where she has been doing her research on identifying biomarkers from the voice in the context of fatigue monitoring in COVID-19 patients and also type 2 diabetes. So Abir, the floor is yours. I'm looking forward for your talk.
Thank you so much, Elisa. I'm happy to be here and to share some of my knowledge, let's say. So today we will be exploring voice AI, as the title mentions, the technologies that are that exist, the algorithms, and and we with this special focus on applications in healthcare. I won't present myself more. Elisa did the job. Thank you so much. So before we start, we need to know already. Okay. What is voice AI? Here I used the photo that you created for communicating the lecture series.
Generated by ChatGPT, actually.
Generated by ChatGPT, I should thank it. So voice AI, as it's known, refers is artificial intelligence systems that understand and generate human speech by leveraging machine learning algorithms to interpret spoken languages and respond or take actions based on that input. It should be also important to know that there's a confusion between AI voice and voice AI. AI voice is one of the technologies in voice AI, and this can't be, they are not the same. But again, now we're talking about voice. Voice is a sound. And what is a sound? What is its constitutes? What is its domain? So first, as this is definitely a normal thing that we could know, that it's a wave that is progressing and the signal progressing over time. So it has a time domain. And here we can represent it with a waveform, which is the amplitude based on the time. There's also the frequency domain, because the signal consists of many distinct frequencies that are expressed as the sum of these frequencies. And here we can have the spectrum, which can be obtained by applying Fourier transform from the time domain and get the spectrum, which is the magnitude based on the frequency. But the sound itself is more complex than the time domain alone and frequency domain alone. It's a composition of both. It's time and frequency. Since the signal itself and the spectrum itself varies over time. So the frequencies varies over time. And here we are talking about, again, time frequency domain that is obtained by applying short time Fourier transform from the time domain. And we can have now the spectrogram, which is a fingerprint or like a visual representation of the frequency based on time and the x-axis. And here we can see these horizontal lines represent the harmonics, and the intensity of the brightness of the color of these harmonics represent the intensity of the signal within that frequency. From these domains, we can extract thousands of actually voice features. And here I will be only presenting some of them that are commonly used to describe the voice and the signal itself. I have to mention that nowadays, the most commonly used packages and softwares to extract these audio features are OpenSmile and Pratt Parcel Mouth. Again, I won't detail all of them. I will be just going through these three. So the pitch, we can retrieve the pitch, which is in the time domain, that measures the average rate of the vocal volt, and we can use it to analyze the variability and the control of the voice. There's the shimmer, for example, that it measures the amplitude variation from cycle to cycle, and that assesses the quality of voice and the potential of vocal fold pathologies. There's also the intensity, as I said now, which represents the loudness and evaluates the vocal strength and effort. These audio features we can use to feed machine learning algorithms to train for classification tasks or regression tasks or whatever from scratch. But not only that, we can also use the spectrogram that I've just shown to train deep learning algorithms also, which are the most commonly used. So we transform the signal to spectrograms to feed them into CNNs, convolutional neural networks, to get the feature maps, and then if we want to have a classification, for example, we can add the fully connected layers, or if we want to have other applications and develop other technologies like generating text from speech, we can use the long short-term memory, which is a recurrent neural network. Now I said that we can use these features and the spectrogram to build algorithms from scratch, but we can also apply transfer learning. And this AI domain is used actually when we lack, for example, or we have a very limited sample size. So we use transfer learning. What is it exactly? It's, as its name says, it's transferring the knowledge of a learned task, so a task A, to a task B. And this is done actually by a pre-trained network. So a network is trained on a task A, and then we can use it to either fine-tune it on a downstream task with our new data and retrain it to have later on the predictions on the task B, or we can extract embeddings or features from these pre-trained networks and then feed them to machine learning algorithms to train them and make our predictions on the task B. Here I present the commonly also used pre-trained algorithms on audio signals, like the VGG, which is pre-trained on YouTube. It's not videos, they converted the videos to sounds with 80 million sounds, and they pre-trained the VGG-based architecture in order to get an embeddings extracted with 128 dimensions. There's also the BioLS, for example, algorithm that is pre-trained on a self-supervised way, which is on only audio set speech recordings, not all the audios that we can find like in YouTube, but only speech-related voice sounds or audio recordings. Now we can where we can apply these technologies and where we can apply these kind of predictions and methodologies. These are the commonly and like booming applications and existing technologies like the speech recognition that converts spoken languages into text, the speech synthesis, the natural language understanding, where we can interpret the meaning behind the spoken input and respond to it appropriately. There's the voice cloning, now that we discussed previously on the ethics and how AI is taking over. Yeah, there's the vocal cloning, where we can create the digital replica from a person's voice from a sample size, from a small sample. And here, the main objective that they created this is just to help, for example, people with voice impairments to well communicate with their loved ones, or like if they want to communicate in presentations or whatever, not for bad applications. We can also recognize emotions by analyzing vocal patterns and detect the emotions within speaker's voice. But also, now we talked about emotions that can take part of health also, and these technologies are applied in the digital health field. What is digital health? It's a field of knowledge, of practice associated with the development and the use of digital technologies to improve health. Currently, we have a lot of connected devices we can use already in our daily life, like the smartwatch, like our smartphone, to track our sleeping, to track our heart rate, etc. And these actually digital measurements, as I said, they are like directly related to the biological characteristics like the heart rate or blood pressure, or if we talk about diabetes, there's the glucose monitoring devices. And this is what we call digital biomarkers. And yeah, this is actually the focus of our group, which is the Deep Digital Phenotyping Research Lab, which its main objective is to pave the way for modern real-life healthcare research studies by being the interface between AI and epidemiology, digital phenotyping, and digital biomarkers, where we actually working also on voice as a biomarker. But yeah, again, why voice in the first place? Because voice is a natural and energy efficient and cheap to collect from real life. Already everyone has a smartphone where we can record our voices, and we can use that on daily basis already. And it can be actually used then by for remote monitoring and telemedicine, and we can use it then if we develop vocal biomarkers as a proxy to monitor treatment and the effectiveness in real life as digital clinical endpoint. But before we go further to the voice biomarkers, we need to know already how voice is produced. I'm sorry, I would just like water. Already, maybe you could notice that my voice changed before and after drinking water, because already I'm super stressed now because I'm presenting in front of you my work. And with the stress, I have my heart rate that is speeding, and then I have this kind of dehydration. I'm losing fluids, and also my throat that is dehydrated, and thus we can express stress already from voice. This is actually how it's done in general. So back to the voice mechanism, it starts with it's characterized by 3 different levels. The cognitive level, where the speech is a speech process starts to be planned, and then get leverage the instructions to the physiological level to the muscles in order to make the vocal cords vibrate, and the sounds will be shaped into based on the vocal fold shape. And finally, it will go through the lips, and the sound is produced, and we will have the acoustic level. Back now to the voice biomarkers or vocal biomarkers, I will start by defining it, which is the vocal biomarker is a signature, a feature, or a combination of features of the voice audio signal that it is associated with clinical conditions. And we can use it, as I said earlier, to monitor patients, to diagnose a disease or detect a symptom, to assess the severity of a disease stage, or monitor the effectiveness of a treatment. Here I present the general pipeline of how we can go from collected audio samples to integrating vocal biomarkers in digital devices. So first we start by collecting voice recordings with vocal tasks, specific vocal tasks that are annotated with clinical data that are filled questionnaires from participants or patients. We then process the data, pre-process it, we harmonize its quality to filter the noise and its quality, and basically we then do feature extraction and feature engineering. We feed the feature extracted and selected to machine learning algorithms or deep learning algorithms in order to identify the vocal biomarker candidates. And then in order to validate this vocal biomarker, we need to replicate it on external data sets and validate the findings on external data sets. And once this is done, we can integrate the vocal biomarker in digital devices in order to have a use in the clinical research and epidemiology for remote patient monitoring or diagnosis of severity or grading tool. But currently, there is no clinically validated vocal biomarker yet. And I will be talking about this because of the challenges that we are facing within the field. Some already vocal biomarkers have been defined mainly for neurodegenerative diseases like Parkinson's disease, where they could use the sustained vowel phonation, for example, as a vocal task, and the pateka, pateka, pateka. Okay, this vocal task, it has a name, but it's super, for me, it's super difficult to pronounce it already. And I don't have any neurodegenerative diseases, but yeah. So they use this pateka, pateka, pateka to study the speech rate and the formants and the way the people are articulating the sound. Voice disorders also, they use the sustained vowel phonation or reading task, and they could found that the people with voice disorders have increased shimmer and reduced harmonic to noise ratio, and they have a change in speech and intensity. So they have fluctuations in the speech and intensity, in the pitch and intensity, sorry. Now back to our work and what we are doing within the lab. Like everyone started working with the pandemic, with the COVID-19, we focused on studying the symptoms within people with COVID-19. We worked on the symptom resolutions, which means we checked if the people with symptomatic or asymptomatic stages have different vocal characteristics, which was the case. We also studied the fatigue symptom, and we studied the loss of taste and smell symptom. Then we CoLive Voice started. CoLive Voice is a project that is worldwide and multilingual. Actually, currently there's English, French, Dutch, and Spanish, but we just integrated also Arabic and Portuguese. So if you want to participate also, so it's an audio bank and with annotated clinical and health data. And it's meant to be a screening platform to identify various vocal biomarker candidates for diagnosis, risk prediction, and remote monitoring. And as you can see here, there's a distribution of the different participations we have in CoLive Voice. I will present now some use cases that we worked on with CoLive Voice data. Here is a special use case by Dr. Vladimir Despotovich, where he studied the vocal characteristics between people with bad respiratory quality of life and people with normal or good respiratory quality of life. Here is presentation of the spectrograms. On the left side is, we can see, is how to say, a fingerprint of a normal sustained vowel phonation, how a sustained vowel phonation can look like on a spectrogram. It's very straight. The harmonics are there. The voice is clear, and the vowel phonation is well sustained. Compared to the person that is with the same age and same gender, with a very bad or impairment in respiratory quality of life, where we can see there's a discontinuity in this in the sustained vowel phonation, and there's also a fluctuation in his voice. These variations of the harmonics are the fluctuations in his voice. Next, this is more special to me as a work, which is working as for vocal biomarkers on type 2 diabetes screening. Here I just need to say that we don't want to use voice as a screening tool for type 2 diabetes. It's more of a first line or at-risk prediction of people with type 2 diabetes. And for that, we wanted to benchmark a vocal biomarker, which is based on a text reading, against the American Diabetes Association questionnaire, which is assessment, which is a risk assessment of having type 2 diabetes, which is like only 7 questions about age, BMI, history of type 2 diabetes, and is actually highly weighted on age and BMI. So the more you are old, the more you have risk to develop type 2 diabetes, and the more you have obesity or like higher BMI, the more you get a higher risk of developing type 2 diabetes. But already, what's the link between type 2 diabetes and voice? Why people with type 2 diabetes have distinct vocal characteristics from the rest of the people? Already, there's the neuropathy that is related to the diabetes that can involved the production of the speech that causes acoustic parameters on an individual voice to be altered. There's also the chronic hyperglycemia in people with type 2 diabetes that result in damaging the pulmonary capillaries, and thus we have a fatigue in respiratory muscles that can prevent a person from inhaling and exhaling adequate volumes of air. Not only this, but type 2 diabetes is a multifaceted disease that comes along with a lot of comorbidities, with a lot of risk factors like hypertension, age, and BMI already that are highly associated with voice, and lifestyle factors. So what we did, from the Colli Voice participants, we selected only participants that are coming from US English speakers, US participants. We worked on each gender separately, females and males, in order to reduce the biases already, because males and females have distinct vocal characteristics already, but they also perceive and experience the diseases in a different way. We matched the control group with people with no type 2 diabetes in order to reduce the challenges of working on imbalanced data sets. And from these participants, we collected text reading recordings that we have pre-processed already. We harmonized the quality and checked their quality. We extracted features and we scaled them, and here we used the first one with the handcrafted features from OpenSmile that we extracted up to 6,000 detailed descriptors, and we compared it to the hybrid BioLS algorithm, which I defined earlier, which is a pre-trained speech-related audio set segments and is adapted to use also OpenSmile handcrafted features and the data-driven features from the pre-trained algorithm BioLS. We then reduced the dimensionality. You could see already that the number of features from OpenSmile and the dimensions of the embedding dimension is quite high, so we need to reduce the dimensionality to avoid overfitting and poor generalization. We used PCA for BioLS embeddings and select K-best for OpenSmile. We used pipeline models to ensure no data leakage, and we fine-tuned different machine learning algorithms with the grid search, and we did a cross-validation to evaluate the algorithms, and we selected them based on mainly sensitivity and specificity. And the most important part, at least for me, is that we performed a performance stratification by key subgroups. As I said earlier, type 2 diabetes comes along with comorbidities, demographics, and like a lot of risk factors that can affect already voice. So we wanted to see this influence of these key subgroups on the performance of the algorithm that is classifying type 2 diabetes status. And for this, we used bootstrapping technique on 1,000 samples. Then, to benchmark the performance of the algorithms, we used Blunt-Altman analysis to study the agreement between the new measurement based on voice against the other risk assessment. So for the results, we found, here I presented the AUC. You know, as AUC is not like the perfectly reliable, as I said, precision, specificity and sensitivity are the best reliable metrics in this case. We found fair to good performances. We could see here in the box plot with the predicted probability and the type 2 actual type 2 diabetes status that there's a quite nice sensitivity in distinguishing between people with type 2 diabetes and without type 2 diabetes. And for the key subgroups, which was really interesting to see that the presence of hypertension for both females and males increased the performance of the algorithm to classify people with type 2 diabetes, or no. There's also the age factor here for females, where female older than 60-year-old had better performances, where the algorithm had better performances to classify females over 60-year-old with type 2 diabetes. And finally, with the Blunt-Altman analysis, we find good agreement for both genders of 96% for female algorithms and 93% for male algorithm. As a takeaway from this case, the study here is only highlighting the potential of using voice analysis as a first-line non-invasive scalable screening method for diabetes. It shouldn't be confused, and we shouldn't be relying only on voice to screen type 2 diabetes. There's the blood analysis that does the job already, but it will at least increase the number of undiagnosed patients. That is half of the population currently. So half of the population is undiagnosed with type 2 diabetes. Future studies need to target early type 2 diabetes, because currently we are working on people with type 2 diabetes. So we wanted to just check already if we can classify people with type 2 diabetes from people without. So studies with early stage type 2 diabetes and pre-diabetes with longitudinal data can extend these findings, and we can study this on broader population also. While expanding these data sets, we need to also understand the nuanced factors of the comorbidities and how they would perform the voice-based screening tools in predicting type 2 diabetes. Now, the challenges, why we don't still have any clinically approved or validated vocal biomarkers. It's a wide range of challenges already. There are the biases that we need to overcome. There's the language biases, gender biases. Already in language only, even the dialects can be biases. There's the reproducibility crisis, when we can't replicate or reproduce the findings on new populations. We don't have still access to high quality data. We are unable to implement in clinical research and practice, and we don't have a specificity to voice features, since also most of the algorithms are kind of black boxed, and we can't interpret or explain what's happening there. Although where we can see the vocal biomarker, once validated and once we overcome these challenges, we can integrate them into medical devices. We can use them for telehealth system, for monitoring, and we can apply them for clinical research as real-life remote patient monitoring and decentralized trials. But voice alone won't have the best performance alone to reach the precision health and precision medicine. We need to integrate more dimensions, more models other than voice, in order to have the better performances for diagnosis, for treatment monitoring, etc. And with this, I thank you so much for your attention, and I really invite you to donate your voice to Collide Voice so we can have more data and to work on. Thank you so much.
Thank you, Abir, for your very, very interesting presentation. I think there can be questions from the audience. So anybody who wants to ask question, just switch on your microphone and ask question, or raise your hand if you like.
Hello. I'm
Hello.
Vasily.
Hello,
Thank you
Vasilis.
hello, Jakub. Thank you very much, Abir, for your very nice presentation. I wanted to ask a few questions. First of all, is it true that my understanding is that you convert the voice to an image first in order to process it with neural networks? Is that correct?
We can do both. We either consider the spectrograms as they are,
Mhm.
or we can convert them to images, and we can actually use CNNs for the images. And we can actually also use pre-trained algorithms on images, like VGG16, for example, on ImageNet.
I see.
Yeah.
Is there like any loss of information when you convert from the audio signal to an image?
This is a tricky question. It depends on the resolution already of the image that you are creating, and
Okay.
it depends also on the sample rate and the quality of the audio signal itself. If you have a poor quality of audio signal, you won't have good spectrograms no matter what you do. So you won't have any good images
I
in
see.
any case. So the audio itself need to be in a good quality in order to have better performances with spectrograms as images themselves.
I see. I see. And have you compared the two approaches, one with CNNs and the one that directly processes the audio signal to see which one is better?
Yes, I didn't present this here, but we worked on, as I said, the fatigue symptom in people with COVID-19, and there we compared the performances of algorithms pre-trained on images, and we used the spectrograms for that, against the features that we could extract from OpenSmile, and it was performing even better. And I can share later on the paper that you can read. There's also the shared code for that, and yeah, we found better results with pre-trained image pre-trained algorithms.
Okay, that's really interesting. Yeah, I would like to see that paper if you could share it. Okay, thank you.
Of course. I will send it
Sure.
circulated. Thank you.
Okay. One more question then. You did mention fine-tuning at some point,
Yes.
like optimizing the hyperparameters of the neural network, I assume, like the number of layers or things like that. So in my experience, this is a notoriously difficult problem. You said you used like grid search to do that. How many parameters were you considering during that process?
Okay, so we worked on multiple machine learning algorithms to compare them already, and for each algorithm, like I will state some: the logistic regression, support vector machine, multi-layer perceptron from scikit-learn. So we fine-tune their hyperparameters, and then we also fine-tune the number of components from the PCA reduction and the number of features to be selected within the grid search tool.
Okay, and that happened numerically, right? You did not do it through trial and error.
No.
Okay.
It was numerically done with the grid search.
Okay, very good. And how intensive was that process? Like how many hours, days are we talking about then?
Of fine-tuning, you mean?
Yeah.
Okay, now I think you can see the number of participants we have. It's in hundreds, so it didn't take much. It didn't take days to fine-tune machine learning algorithms.
I see. Yeah, that makes sense. Okay.
Yeah.
Thank you very much. It was a very nice presentation. No problem.
Sahar, you wanted to ask a question?
Actually, just for CNN, you feed time frequency. It was my impression. You
time frequency domain spectrograms. Yes.
So that was the best option for voice to image, right?
Yes.
Your experience.
Yes.
But my actual question was that okay, so detecting diabetes, like one disease against health, is definitely wonderful. Oh, also, sorry. Thank you for presentation as well.
No,
but I mean, okay, so okay, so when it comes to diagnosis, we probably can't tell a lot if we can't tell this person is sick, this person has an illness, right? Because you didn't check all other diseases to make sure
Only
that
type 2 diabetes.
these kind of biomarkers are not specific to the diabetes or something like that. Is it? Does it make sense?
So
Because
the people that we studied here have type 2 diabetes, and they don't have how to say, yeah, they have type 2 diabetes against people without type 2 diabetes. We didn't analyze the rest of the diseases that they can have, but we studied the comorbidities and lifestyle factors and demographics to see their effect on the performance of this classification.
Yeah, but how viable could be the results? Because we don't know if any other health problem can cause the same biomarkers, can create the same biomarkers.
I totally agree. And we try to explain this already with these performance stratification, but that includes hypertension, that includes migraine, that includes depression, that includes fatigue. So we try to explain what works best for this classification, what is influencing more this kind of classification. But yeah, a human being is multimodal already, and that's what I said at the end of the presentation. We can't use only voice, we need to use all the modalities to characterize one disease.
Thank you.
You're welcome.
I have a question, I think related to the previous one. Like, did you study the effect of potential confounding factors, like medication or even other comorbidities that may be also affecting the voice? Like in some sort of vicious circle, like the voice determines the maybe the comorbidity, but the comorbidity may be also affecting the voice. And similar for medication of the patients.
Yes, here I didn't study the effect of medications. Already people with type 2 diabetes, they undertake treatment for type 2 diabetes, so it's super different already from people without type 2 diabetes. I try to reduce the biases as much as possible compared when it comes to languages. So we took native English speakers from US participants. We stratified the genders also. We have same vocal task, and we studied the maximum that we could collect from co-live voice to study these cofactors and confounders on the performance of this classification.
I see. Yeah, just thinking that it may be interesting, something interesting to do, because in the end, like, you need to study these factors so you're sure that you're predicting the disease and not the medication effect or not another comorbidity, something like that.
Yes.
And then something else I'm also curious about is about the data sets you use for training. Like, if I understood well, you took like publicly available data, and then you fine-tune or you generated the embeddings for the data that you're interested in. So I'm guessing that there will be a lot of imbalance between controls. Like, let's say, I guess most of the data sets out there about audio are controls. Like, you assume they don't have the disease. So is this unbalance a problem, or how did you manage to I don't know, like, did you apply any undersampling or like data augmentation technique to compensate for that, or how did you tackle this problem?
Okay. So already to get the embeddings, we use the BioLS, which is a pre-trained algorithm on thousands of segments of speech-related tasks. Okay, it's a self-supervised pre-trained algorithm. From that algorithm, we extracted embeddings, and that we used them to feed machine learning algorithms. That's one part. The other part is when we did select the participants, and you can see here in the slide where there's gender stratification, I mentioned that already we randomly matched the control group without type 2 diabetes to the same sample size of people with type 2 diabetes already to overcome and to not work on this challenge of imbalanced data sets.
I see.
So yeah, to reduce the complexity already of this task, we randomly match the sample size.
Okay. Okay, so you basically it's like some undersampling, like just removing extra samples.
Exactly.
Okay. Makes sense, I think. Thank you very much.
Thank you.
Hi, Naila speaking.
Hello.
Hi, thank you very much, Abir, for this excellent presentation. Very interesting work. I have a question regarding the data as well. Were there any pre-processing that you had to do on the voice recording?
Yes, we have a dedicated pipeline to pre-process our data. It's a real-life setting data. So people on in their houses, wherever they are, they record themselves and participate through their smartphones or laptops. And we did pre-processing pipeline for that in order to check the quality and exclude the ones with bad quality or bad vocal task or wrong vocal task, sorry. So yeah, but I can't really detail much about the pre-processing currently because it's confidential, as it will be a project for a spin-off within the LIH.
Okay, and what were the challenges that you wanted to overcome with this pre-processing strategy?
Already to check that the quality is good of the recordings, which means there's no minimal noise. The people they made the correct tasks. Sometimes people they start recording, for example, before doing the recording, so we need to check already if the time that they started recording is actually the time of starting the vocal task or no. Yeah, this kind of quality assessment we do.
Okay. Also, another question, if I understood well, the participants were mainly individuals with type 2 diabetes?
Yes.
Were there any reason not to include the individuals with type 1 diabetes?
Already type 1 and type 2 diabetes, they are super different, and they both people with type 1 and with type 1 diabetes and with type 2 diabetes, they have already different vocal characteristics and they undergo different experiences. People with type 1 diabetes, they experience diabetes since their childhood, but type 2 diabetes comes with this kind of lifestyle factors and the habits that it's like developed with time. So already the experience is super different. That's one. Two, type 2 diabetes type 1 diabetes is easily diagnosed at the very early stage and, as I said, in childhood, but type 2 diabetes is underdiagnosed. And 50% already of people with type 2 diabetes are not diagnosed with type 2 diabetes worldwide.
Okay. Okay. Thank you. Thank you very much again.
Thank you. Thank you.
I saw Hitchem who was raising hand, but I'm not sure if it is still the case.
Yeah. Hello, good morning, everyone. So thank you so much for this great presentation. So I'm not a health expert, by the way, I'm data scientist. So my question is related to these two previous suggestion or comments about data, unbalanced data set, etc. So when you take, I want to talk about metrics you consider, true positive and true negative. I think in health is not enough. It's the wrong metrics. Why? Because if someone is sick or has diabetes or cancer, If we miss that, it's a big problem. So,
Yes.
as the last person said, maybe there is a specific group very important. We need to evaluate our metric, and based on that, our target group. Not in general, because in general we can make 99% perfect, correct? But we miss one person who had a cancer. Then the model for that class is 0%. The performance of that class is 0%. And this is very bad model. Overall, looks great, but for a specific group or our target group, this model is really performing badly. So this we should take, I think, in consideration. Then for the unbalanced data, there is a lot of techniques already available, but I'm not in favor of that, like undersampling, oversampling, etc. Blah 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 is not enough, because we manipulate the data, we calibrate the models, and we test them in real data set. And when we test them real data set, the model is not performing well. So this as well, there is a new technique, so we can handle this kind of unbalanced classes for medical, I think, for medical issue. Yeah, this is very important, I think. What do you think about that?
Yeah.
Because
I
if we
totally agree with you already. Okay, so I will start to go one by one. Already, for oversampling techniques and generating synthetic data for oversampling, I'm totally personally against that, because we are working already on medical field, and the augmentations might cause these biases and overfitting already themselves, even if we do perform correctly and ensure that there is no data leakage. The other thing is the performance metrics. You said that performance metrics, you don't agree that I chose sensitivity and specificity.
Correct.
Okay, those are general metrics, but we also check the metrics within each class, and we are mainly focusing on type 2 diabetes class to see if the performance of the algorithm is actually, or the algorithm itself is really detecting true positive cases and true negative cases, which are both important.
Okay, that we didn't see in the slide. And then that other metric was really computed from the confusion matrix is true negative and false positive. That's very the error term. This is very off diagonal term. This is very important than the on diagonal term.
Yeah, I agree.
It's very interesting to see them as well. Yeah, thank you so much.
Sure. Thank you.
Welcome.
Just sorry for follow up with what Hichem was saying is perhaps false positives and false negatives have different flavor here, because if we make an error and we qualify somebody as being diabetics if somebody is not, it is not that harmful as if we did the opposite. If we make an error,
exactly, because we will be telling, maybe we will be telling a person that he probably have a risk of developing type 2 diabetes and not having type 2 diabetes. As I said, voice won't be a screening tool, but the first line or kind of triage of maybe you have type 2 diabetes, and go check your doctor and go do check with the blood analysis if you really have type 2 diabetes. I can't see where's it. Yeah, it's not harmful, as you said.
Sure. And I have a question related to the machine learning algorithms themselves. How do you feel they perform with respect to some of the existing methods? I can imagine, because you mentioned in the very beginning that you have some already some prior knowledge about what type of voice anomalies can exist within the population that is sick. So you could think of some rule-based approach that just to, you know, look at the diagrams and trying to figure out who has some anomaly in the voice that are perhaps specific for
type 2 diabetes.
For type 2 diabetes. And my question is, have you made any comparison between the two approaches? Let's say, take the simplest rule-based approach in which you just detect simply some anomalies, and then take the machine learning algorithm, one of those that you tried, and see what is the additional advantage of using machine learning approaches with respect to some rule-based approaches.
We also tried rule-based approaches, of course, to compare, and we start with them before going into AI and black boxes at the first place. We also do statistical analysis on the vocal features that we can extract to see already if we can characterize some vocal features associated to the disease itself or no, before again going to advanced AI applications. So yeah, we do that, and this is performing much better, of course. And that's I'm presenting it, and that's why I'm presenting it. So yeah.
Okay. Okay, I can see no more question. Oh, Hicham, okay. Please go ahead.
I'm really curious because the topic is very hot topic, as she said at the beginning. I'm not health expert again, but I'm really curious. So I know that diabetic could be genetical, caused by environment, like air pollution or whatever, and a lifestyle because we are stressed. I don't know. So can we quantify the different, I mean, the consequences or the portion of each dimension and to be diabetic for the future? So you can build a system not only to classify, but also to maybe to see, okay, your lifestyle is not okay, so maybe in 10 years you'll be, this is your probability to get to be diabetic or whatever. So like for yeah, this kind of tool, I believe it will be very needed. I mean,
yes, of course. As I said, also, I mean, there's already the questionnaire that is used, the other risk questionnaire. It asks about the history of type 2 diabetes, and it's relying on age and BMI. As I said, if you have older or you have high BMI, you have more risk to have type 2 diabetes. But for our context, including early stage type 2 diabetes and pre-diabetes, with this we can characterize these voice changes, and if we check if these three categories, early stage type 2 diabetes, pre-diabetes, and people with experience already with type 2 diabetes, they have different vocal changes, and track them over time longitudinally would be really interesting to see. Yeah, it's important.
thank you.
I can see a question from Nohaila.
Yes, hi again. So I imagine that right now you're in the process of collecting more data, right? And I have a question. Does the language of the voice recording would affect the models? Because there are some languages that maybe have higher pitch. You need higher pitch, or
yes.
Do you have
language
requirements?
Okay, so we already collect multiple languages in Collive Voice, and the more languages we collect, the more reliable and generalizable algorithms we can create. But already language itself is a very big bias for the vocal biomarker development. As I said, language, even dialects differ from like the vocal characteristics differ from different languages and different dialects already. So yeah, currently we worked only on English speakers. We need to validate that on French speakers, for example, or Spanish people, for example, and then also they culturally they experience and they live with type 2 diabetes or any other disease differently. So language only not only, but also the cultural environment, the socio-demographic factors, economic factors. So yeah, a lot of biases that we need to work on.
Yeah, I see. Thank you.
I have another question. Sorry, is there someone else?
No, I just go ahead.
Yeah. So you mentioned in the end that the perspective that you see for the field is to be multimodal and to not be 100% reliable on voice.
Yes.
And I agree on that. And I'm wondering if you have tried to combine vocal biomarkers that you have identified as relevant with other types of data, like molecular data or clinical data or lifestyle, I don't know, environmental, and like to really prove that the models are better with different types of data.
So already in Collive Voice, we collect clinical data only, but we don't collect molecular data or blood samples or whatever. We collect based on questionnaires, clinical variables, etc. We have already tried with the project with Dr. Vladimir Despotovich on respiratory quality of life, where he also showed and added clinical, where he also added voice to clinical features to see if the voice can bring informations to clinical features alone, and it was the case. He had very good performances just by adding voice to clinical features for detecting respiratory quality of life. Yeah. For type 2 diabetes, I didn't do that. Rather, but I did this performance stratification and checked how it works already within the comorbidities and lifestyle factors.
Okay, thank you.
Thank you.
And by the way, Abir, if you like, you can send me the link and maybe this QR code, which we can post on the website of the seminar.
That
So
would be perfect. Yes.
Can advertise this Collive Voice application.
Thank you.
I have one question that is related to the information about this startup or spin-off that you mentioned. And the question is about some legal restrictions within the European Union. Do you have any knowledge of or experience how difficult it is in EU to implement artificial intelligence systems for healthcare? Because as far as I remember, in some early ideas for the AI Act that was already accepted in EU, there were some severe restrictions on the use of AI technologies that are directly related to human. So how is it now, and how it is somehow colliding with the idea of spin-off of that kind?
So the spin-off is relying mostly on the pre-processing pipeline, how we ensure the readiness of voice recordings to be fed to AI algorithms and to develop vocal biomarkers. It's not really AI-based technology that we are using. But for that, I have very minimal knowledge about these kind of approval and ethical concerns from the GDPR and governmental people. So yeah, I don't have much to say here. I don't know how it works now. So yeah, I'm sorry.
Yeah, I remember we had a presentation on the seminar on that legal part. It was around 2 years ago. But the law has changed over time, so I was wondering whether there are any news.
I guess they are now they get more and more accepting the fact that AI should be implemented within different fields and also healthcare. So maybe it's becoming easier to implement such thing, easier by time, kind of. But I can't say more.
Okay, thank you. Sahar, I can see the hand.
Yeah, I just have a comment. I guess the law is only targeting banning emotion recognition in workplaces so far.
Really, because there are some companies now, they are doing emotion and depression status recognition in workplaces. Yeah, they're making for that.
I guess probably when it comes to like a power, I mean, they start to actually execute the rule, but this is the only thing that they it is banned, probably putting a stop on emotion recognition research in Europe for a while. That's it. Thank you.
Good to know. Thank you.
Okay, I think we have 11 o'clock, so we should be slowly ending the meeting. Thank you very much, Abir, for this very nice presentation, and thank
you for
everybody
having me.
for the discussion. Thanks, Elisa, for co-hosting the meeting. We'll keep you posted about the future seminar meetings.
Yes.
I can see some link from Sahar already.
Yeah, about the
perhaps about these restrictions, legal restrictions. So if you want to use it, just click it now, because after we end the meeting, it will disappear.
Yes, so that's why I didn't want to send anything on the chat. I will just send it to you, Jakub and Elisa.
Yes. And I can post it, whatever you think is can supplement your presentation. Just send it to us, and we can post it on the website.
Sure.
So have a good day today, and let's stay in touch.
Really nice to meet you.
Bye bye.
Bye bye. Thank you so much.
Bye. Have a nice day.
Bye bye.